All right, so we want to know, how does the electric field vary with the other variables? So for example, if Q goes up, then the electric field goes up. So if I have a charge Q here, I have a charge 2Q at some other space, they're not related to one another, not in the same area. The electric field here, we would call E1. The electric field over here, E2, it would be twice of E1, just because I've increased my charge by a factor of 2, so it has a stronger electric field surrounding it. Okay, Q is the charge. Okay, so Q is the charge. K, remember, is the Coulomb's constant. Uh, that has a value of 9 to the ninth, but the value doesn't really mean anything for y'all because you're not going to have to calculate the force or the field. I think it might be on your equation sheet. No, it's not even there. It's not even really that important to y'all. Don't get the K confused with the spring constant that we used in a previous chapter. Oh yeah, be careful because those chapters are going to be on the same test. Remember we had the spring constant, the 2 pi square root of like K over L or something, the frequency. Yeah, I'm getting that wrong. What is it? 2 pi square root of K over M for the frequency of an oscillating spring. The different Ks, different values completely. All right, so two main points about electric fields. Forces produce motion. Or excuse me, charges produce fields. When I have a charge, there's an electric field surrounding it. And a force acts on a different charge in an electric field. So if I have a charge here plus Q, there is an electric field in the area surrounding it. And if I bring another charge up next to it, say plus another plus Q, and it will experience a force due to that electric field. Right. That force is given by what we saw before, like this. That force is given by F is equal to Q times the electric field. Whatever this charge is, times whatever electric field is caused by this charge. All right? So when a charge is in an electric field, it feels a force. Let me show you another way we can think about this. We'll look at this later as we look at the cell. But if I think about, I've drawn this picture before, if I think about having two separate distribution of charges, there's an electric field between these charges that go from the positive to the negative charges. These lines just represent the electric field. We call them field lines. If I put another charge in the middle of those two distributions of charges, it's going to feel a force. So if I put a charge right here, it will feel a force that is in that direction. It feels a force due to the electric field. Okay? We'll see that again when we get to the cell, because we'll see that the cell has very large fields between the different sides of its membrane, because you get positive charges on one side, negative charges on the other side, and so you'll have a net force driving ions from one side or to the other. All right, let's look at electric potential energy. So far we have forces, we have fields, and now we're going to look at electric potential energy. Potential energy describes an object's capacity to do work, just like what we had, gosh, like chapter 2, I think, 3 maybe. So charged particles experience forces. If I have a particle here, and I bring another particle here, and I hold them in place, say two positive particles, if I were to let them go, they would fly apart from one another. And so because they have that tendency to fly apart, just like if I have a book that's held up above the earth and I let it go, it moves, we say that it has potential energy, right? We said this had what type of potential energy? Gravitational potential energy. exactly the same with electric charges. In fact, it's remarkably the same with electric charges because you have the same relationships between distance and charge as you do with gravitational force and mass and distance. So they have the capacity for motion. Because they experience these forces, they have the capacity for motion. So we can do a simple derivation for the force, or the work rather. Work is force times distance. Remember chapter 2 or 3? That's also equal to our potential energy. Because work and energy, you know, that whole work-energy theorem, if I do work, I change an object's energy. That's equal to the force, K, Q, Q over D squared, that's Coulomb's law, times the distance, which is D. And so that gives us the expression for U. U, the potential energy, equals K, QQ over D. Notice I just got rid of one of these D's right here. They cancel out. So that's sort of a rough derivation of how we determine the potential energy of two or more charges. So what this says is, if I have two charges, Q right here and Q right here, separated by a distance D, and they contain this amount of energy. So U is equal to the potential energy. Again, you're not going to have to calculate it, so you don't need to worry about what K is. It's just a constant. But this energy is proportional to each of the charges. So if I increase this charge by a certain amount, then it increases the energy by the same amount. It's also inversely related. It's not an inverse square relationship, but it's an inverse relationship with the distance. So if I move those particles farther apart, what happens to the force as I move the particles farther apart? Does it increase, decrease, or stay the same? The force decreases. In fact, we know the force decreases a lot. If I double the force, by how much? If I double the distance, by how much does the force decrease? Not twice. It decreases by a factor of not 2, but 4, because it's an inverse square relationship. So if I square D rather, then I decrease F by a factor of 4. Okay, so here we can have positive or negative energy. Two like charges have a positive work. You have to work to bring them together. Two positive charges here. They feel an attractive force or a repulsive force as I'm moving them closer. Do they feel attractive or repulsive? Two positive charges. Repulsive. Like charges repel. So as I move these charges together, I have to push on them. I have to do positive work, pushing in the direction of the force or in the direction of the displacement. My force and displacement in the same direction. Remember, work, F times D. I have to push them in the same direction in order to get them to this position. And so they have then, because I've done positive work, they have positive potential energy. I can think about if I let them go, they're going to fly out across the room. Now, negative charges, or if they have opposite charges, so here is a negative charge, and here is a positive charge. As I bring these together, moving them in this direction, what do I have to do? Do I have to force them together, or do I have to hold them back? These are opposite charges. Opposite charges do what? They attract. So left to their own devices, they would suck up next to one another because that's what they want to do. So in order to move them to a certain distance from one another, I have to like hold them back. It's like two dogs trying to get at one another. You ever walk a dog and it comes up to another dog? You ever do that? Yeah? Listen, we have a 100-pound dog. And like if he sees another dog and he wants to go there, lickety split, he's over there. But he's a very obedient dog, so you just tell him not to. But anyway, charges aren't so obedient. as they come up, you have to physically pull back like two pit bull dogs that are trying to fight. You have to pull back on them. So they're going in this direction, but the force is in the opposite direction. And so that's negative work. So for opposite charges, you have to do negative work to keep them apart. And so that means that they have negative potential energy. So if they have opposite charges, they actually do um, they do work on you because they experience an attractive force. And if you want to think about the dogs, right, you got a dog here, leash, you're applying a force in that direction, but the dog is going in that direction, so that's negative work. And then likewise over here, you got the other dog. You're applying a force in this direction, though the displacement is in that direction, the distance that you're covering, and so that's also negative work. But that comes out in the equation for you. Just a second, Zach, let me make this point. That comes out in the equation for you because if I have two positive charges, I have positive potential energy. If I have a positive and a negative charge, I have a negative potential energy. That's where that idea comes from. Your book describes this some in the chapter, but think back about work and how these forces are related to one another, and also, the charges. Zach, what was your question? You have to do positive work to bring them together. So two positive charges, you have to do positive work to bring them together because you're pushing in this direction and you're moving them in this direction. Work is force times distance. When the force and the distance are in the same direction, then you have positive work. We're going to get to that, but yeah, that's similar. We're not going to get to the mechanism of the sodium-potassium pump, but we'll talk about how that moves charges back and forth. And one of them very much has to do with the potential energy. Okay? Students sometimes have a bit of difficulty with this. So I would spend a little bit of time outside of class rereading the sections in the book. Sometimes I read something and I don't understand it the first time, and then I read it again. And sometimes I have to read it 3 or 4 times before I ever actually get it. So that might be true for you too. It's certainly true for me. So it's probably true for you as well. All right, so both force and energy decrease as the distance increases. So as d goes up, F goes down, and U goes down, though at different rates. Because remember, F is proportional to 1 over D squared. If I double D, F goes down by a factor of 4. But energy is proportional to 1 over D. So if I double D, then I have the potential energy. All right? Make sure you understand those relationships because you'll certainly see some questions like that on the test. What happens when you double the distance between two charges? What happens to the force? What happens to the field as you move away from a charge? And being able to look at the equations on your equation sheet, don't even memorize them, they're there, but just be able to look at them and say, well, gosh, well, F is KQQ over D squared, so if I double D, that means my force is going to be 1/4 its original amount. You'll see those types of questions on the exam. I think it's in about a week and a half or so, if I'm not mistaken. Yeah. All right, so when D is very large, we would say when D approaches infinity, when it gets really, really big, as you move farther and farther away, both U and F are 0. If I have two charges right here, they feel forces in this direction. Say this one's negative, this one's positive. As I move them farther and farther away, like my negative is here, my positive is over here, the force is basically 0 because I've increased my distance so much, that now the force basically goes to zero. So when you move those things apart, they don't feel any force, and because they don't feel any force, there's no potential energy. Right? An object that feels a force is one that has potential energy because it has the potential for motion. Okay, so charges move in electric fields. And generally, they prefer to move in the direction of decreasing potential energy, like a ball rolling down a hill. So I drew this figure for y'all before, but I think it'll help you to sort of think about this. I have a mountain. I put a ball on the mountain. It's a positively charged ball. Is the ball going to roll uphill or downhill? It's going to move downhill. Right, that seems obvious. It'll move in that direction. It's moving from a position of high potential energy to low potential energy. And that in general is what charges do, at least when we're talking about positive charges. We'll see later that negative charges do the opposite. But just in your mind, imagine, okay, positive charges, they're the ones that do it the way we think of it, right? That they will move from high to low potential. They will move from where it has lots of potential energy to where it has not that much potential energy. So charged particles in the body similarly will move from areas of high potential energy that's our value for U to low potential energy. And I'm going to write here positively charged particles. Positive particles. Those are our, what are those? Our anions or cations? Those are cations, right. What do y'all use to help you remember that? Anybody? Y'all just remember it? You just know it? Okay, because y'all are smart like that. Okay, so let's try these questions. Generally, objects move in a direction in which their potential energy does what? All right, we'll stop at 23. 23. Go ahead and do the next one. Look at y'all. That's awesome. Let's go ahead and do this one on the right. The electric field is a measure of what per charge? Is it potential, mass per charge, energy, or force per charge? Potential per charge, mass per charge, energy per charge, or force per charge? All right, let's stop at 27. 27. Okay, very good. D is right. It's a measure of force per unit charge. Remember our electric potential, our electric field is defined as F over Q. You have forces, you have fields, which are force per unit charge, and then next we'll have potential, which is energy per unit charge. All right, let's look at electric potential. Oh, did y'all read that in the paper? It was in the comment yesterday. There's this guy. It's terrible. He was in an accident. It's not funny, okay, because he lost like his left arm and his left leg cut off completely. He's all right now. I'm sorry, I blew that one. I was going to totally make y'all think that was a real story. All right, so electric potential is a measure of energy per charge. We got forces, we got fields or forces per charge, and now we're going to have potentials, which are energy. Let's write it as U. Potential is U per charge, electric potential energy. So we're going to define then our potential as U divided by Q. It's measured in volts. So we could look at the units. We could say the units for V are 1 volt. You've heard this before, a 9-volt battery. That describes how much energy per charge is given to those electrons before it sends it off into your whatever. 120 volts over here, that sort of business. 1 volt is equivalent to 1 joule per coulomb. We'll just stop there. There are other ways we could express it, but remember, energy is in joules, charge is in coulombs, so we could think of that also as joules per coulomb. It's often referred to either as potential, voltage, or potential difference. And we'll sort of use these interchangeably. They're not exactly the same, uh, as we'll see. We'll be able to calculate the potential, kind of like we did for fields, for a single particle, or for a single position in space. However, the potential difference is the difference in potential between two different points in space. And so they're similar, but they're also different. All right, so since potential is energy per charge, we can develop an expression. This is just U over Q. So we know U was KQ Q over D. And then we had another Q because we're dividing it by, just like we did for fields, right? But for fields, we did Coulomb's law over Q. And so I can cancel out one of my Q's, and I get my potential is equal to KQ over D. This is on your equation sheet, should be. Yeah, it's on your equation sheet. All right, so if Q is positive, the potential is positive. If it's have a positive value, um, if D is large, what happens to V as I increase D? If I increase D, what happens to the voltage? It decreases because I have that inverse. So V is small. And if Q is big, if I increase Q, what happens to V? It increases, right? It's a linear relationship, so V is big. So understand those relationships, inverse or direct relationships. Often we're interested in the potential difference. Which is the difference in the potential of two different locations. So imagine my mountain, like the Alps or something. We're going to the Alps this summer, did I tell you? Well, we're going to Europe. We're going to be there for about 3 weeks. We're going to see family in Finland for about a week. My wife's from there, or her mom is from there. She was born here. And then we're going to go to Paris, and then we're going to Germany. In what? In Germany, we're going to Mannheim. We're going to Bacharach, and we're going to Fusen. And in Fusen, we're going to go up into the Swiss Alps and sort of go up in the mountains and hang out for a couple of days. It's going to be, chilly at night, I'm sure. It's going to be like 95 degrees here. It's going to be June. We'll be there in June. Now, we went to Finland about 10 years ago, and it was like 80 degrees there during the day. And those people there, they literally thought they were going to die. They were just, everybody, they had these warnings about how hot it was. Old people were just sitting in front of fans. It was like here at 110 degrees. Hmm. Right. Yeah, well, they don't have air conditioning there, so that's part of it. All right. So what was I saying? You're distracting me. Yeah, I'm sorry. The Swiss Alps. Yeah. So a potential difference, what is the difference between this point and this point? That would be sort of like what is our potential difference. I want to know what is the difference in energy per charge between these 2 points. And we'll see that like with our graded potential and our action potential later. You probably read about it. Hopefully you read about it already in your cell and the neurons that we look at a potential difference between 2 points. So if a particle moves from point 1 to point 2, where say this is my initial point, this is my final point, then my delta V is equal to V final minus V initial, which is V2 minus V1. And we could calculate the actual values. Like let's say that, I don't know, let's say that this is 4 volts. And this would this be a bigger at point 2? Would it be bigger or smaller at point 2? Yeah, it would be smaller. What would the value be at point 2? Would it be 2 volts or 1 volt? I move twice as far away, right? Here I have 4 volts. I'm this distance away, and then I double that going to point 2. Is it going to be 2 volts there or 1 volt there? Let's do it as a clicker. All right, so is it going to be A, 2 volts or B, 1 volt at that point, at point 2? All right, let's stop at 39. All right, so let's think about our potential. Our potential is equal to K Q over R over D rather, excuse me. If I double my D, what happens to my voltage? I've doubled it, right? So what happens to my voltage? Does it increase or decrease? I just heard creases. What is it? You sort of mumbled the first syllable. Does it increase or decrease? Decreases, right? So it's going to go down. Is it going to go down by a factor of 2 or a factor of 4? 2. Thank you. Right, because this is not squared, right? It's a linear relationship. It's an inverse linear relationship. So if I double this, I'm going to have this. So if I move from this point out to this point, twice the distance from this charge, I'm going to go from 4 volts to 2 volts. Yay! All right. It's an inverse linear relationship. You're going to see some questions like that on the test, okay? So did I mark A? Yeah, 2 volts is right. Okay. Batteries are labeled according to their potential difference. It's the difference in potential between their 2 terminals. So this would be delta V. The difference, like, think about my mountain. This is the high side of the mountain. This is the low side of the mountain. And charged objects are going to move from the high side of the terminal. They're going to go through your circuit, through your Walkman radio or whatever it is that you have. And then, you don't use Walkmans anymore, do you? No, yeah, because you have iPods and stuff. Back to the to the other terminal. It's going to roll down the hill, the charge. Okay? Potential difference. Next time you're talking about batteries and somebody asks you, instead of saying, I don't know, what is the voltage of that battery, you say, what is the potential difference? And they'll think that you're cooler than, I don't know. And you really are. But y'all are pretty cool people. All right, so let's look at electric potential difference and potential energy. Well, there's our cell membrane. We'll get into that sodium potassium pump later. But imagine a charged molecule or atom, and an ion, cation or anion. It moves between two different points, perhaps across, say, I don't know, a cell membrane. And it experiences a potential difference because I got, gosh, what is this on this side? Are these positively charges over here? I can't really see it. Well, it's not that important right now. I have a bigger figure later. Well, it doesn't matter. All right. All right. One side is more positive than the other. I forget which it is. But we're going to have charges that are going to move back and forth because of these difference in potential. So it experiences a potential difference in the energy of the charge that passes from one side to the other will change. And that energy is going to equal to Q, which is the energy of the charge, or excuse me, the magnitude of the charge. How big is the charge? Is it 2 coulombs? Is it 3 coulombs? What is it? Times the change in potential. So I have my V final on this side, my V initial on this side, my charge moving from here over to there. It's going to experience a change in energy because it's moving across this change in potential. In some cases, it might gain energy. That is, if delta V is positive and Q is positive, or sometimes it might lose energy. That is, if delta V is negative and Q is positive, or vice versa. All right, charges tend to move to, where am I? They'll tend to move to lower potential energy. Or we're using U for potential energy. So this delta U will tend to be negative. Right? Remember your mountain. As I have an object moving from this point to that point, delta U is a negative value because my U final is small, but my U initial was big. So I'm doing a small number minus a big number is going to give me a negative number. Then positive charges will move so that delta V is negative. That means decreasing potential, while negative charges will move so that delta V is increasing, positive potential. We've already said this. It's on our mountain over here. Positive charges go from decreasing potential, high to low. Negative charges, on the other hand, will move in the opposite direction. And it all is because charges will tend to move towards a lower potential energy state. Everything tends to move in that direction, a lower state of potential energy. All right, it's possible to move charges so that their energy does increase. That's their U. Notice, look, this is the opposite of what I just said. Okay, We just said that charges tend to move to lower potential energy. But it is possible to move charges so that their final energy state, their potential energy, is bigger than what it was before. However, this requires some source of energy, like when we move an object like up in the gravitational field. So if I have this thing and I let it go, it's going to tend to lose its potential energy. I can cause its potential energy to increase, but I have to actually physically move it up in the gravitational field. Okay? That's different than what we're writing over here with the negative charges. Negative charges tend to do this. When they move up in potential, they're actually losing potential energy. I know that's because they have that whole negative thing going on. So they're sort of wonky that way. All right. Soon we're gonna wrap up soon actually. I'm gonna let you out a little bit early today if that's okay. I'm sorry. I know that we got a late start and you had the quiz, but I have another meeting to go to. I need to. No, it's okay. I'll just forget about the meeting, right? All right. We'll go on to capacitance a little bit. This energy then in cells is to move charged. Where am I? I'm sorry. Oh, to move charged ions, cations or anions, so that their potential energy increases. Comes from the sodium-potassium pump, or NAK pump. We'll talk about that more later when we get into the anatomy part of this section. We talk about neurons, but in the cell. But you can think of that as being like the chain on the roller coaster. Chugga, 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 chugga. That's your sodium-potassium pump. What does the sodium-potassium pump do? What does the sodium-potassium pump do? Thank you, Kai. I think that was you. Was that you? Came from over there. Chugga chugga. That's your sodium potassium pump. They're like picking up those charges and giving them energy and moving them to another place. And so it's aptly named to be a pump. Okay? Let's look at capacitance just for a few minutes. Capacitor is a device that separates positive and negative charges. It typically consists of two metal plates that are separated by an insulator. So like this is a little figure of a like a cartoon version of a capacitor. You have two metal plates, and then usually you have an insulator in between them. Although air is an insulator, so you don't have to. You could just have, just space in between them, or air, or nothing at all. Just something that doesn't conduct electricity. When connected to a source of potential, actually when it's connected to a source of potential difference, or delta V, electrons travel from one of the plates to the positive terminal of the battery. Remember that negative charges move from low to high potential. And then that plate is positively charged. What that means is, look, I hook these two metal plates up to a battery. Electrons from this plate has electrons and protons. Some of the electrons are going to travel down the wire and go onto the battery. And then other electrons are actually going to travel over to this plate. So we'll get electrons that will move away from this plate, and then we'll get electrons that move towards this plate. And the end result is that I have a positively charged plate and a negatively charged plate. Okay, so because that plate is positive, Electrons from the other terminal of the battery, or from the negative terminal of the battery, travel to the other plate. I get electrons coming here, and then I also get electrons going there. So I get a positive plate and a negative plate. Why don't we stop there? Actually, no, I'm sorry. So then each plate has equal but opposite charges. We're still in this last thing. All right, we will stop there. Again, I'm sorry for